Hey guys, so this is gonna be a video on how I solved the 8th European Math Cup Senior Division problem number 3, which is geometry, which is kind of my forte right now, I guess. So yeah, we just had the contest earlier this morning for the Philippines, and this was the only problem I got to solve. I didn't get to solve numbers 1 or 2, and then 4 is probably just really hard, I guess. And yeah, so right now it's December 20, but I can't post the video now yet because it's one of those Olympiads where you take it to your home country and send it to the organizer. It's not allowed to be discussed online until the official problems and solutions are posted online. And of course, they're not yet posted, so I can't post this yet, but I will eventually. I'm just videoing it now because the solution's still fresh in my head. Insight, motivations, whatnot. So yeah, the statement of the problem. The statement of the problem is, so you have acute triangle ABC, AB and AC are not equal. I is incenter, O circumcenter. And then the incircle is tangent to BC, CA, and AB at DEF. And then prove that the line passing through I parallel to EF, that line, the line passing through D parallel to AO, and then the A altitude are all. Prove that if those three lines are concurrent, then their point of concurrency, I labeled it as K here, must be the orthocenter. So yeah, when I read it, I was like, frick, weird geometry. I don't like, my weakness is like weird geometry. I prefer geometry with more standard conditions. A random concurrency like this is a really weird condition to handle. So yeah, but anyway, since I wasn't really making much progress on numbers 1 and 2, I decided to try it. And yeah, eventually I solved it, which was good. So the first thing I did, my instinct told me, because, you have orthocenter, incenter, circumcenter. Then like, line KI joins two of them. So I thought, maybe there's a meaningful way to relate those 3 points with something else. And I remember that if angle A is 60 degrees, you get B, orthocenter, I, O, and C will be concyclic because all their angles is going to be 120 degrees. So yeah, in my first drawing, I drew it at 60 degrees. I drew with the compass, then I put a point there. Same length as radius, boop, boop. That's how you draw a 60-degree angle in a circle. And then so, when I drew it, they weren't exactly concurrent. And then also this is where I noticed something. So like, obviously AE equals AF. And AI is the angle bisector there. So obviously, EF is perpendicular to AI. So it's basically AI is perpendicular to IK because parallel. Points E and F can be removed. Basically, AI perpendicular to IK. And yes, the solution actually doesn't really use points E and F. They're just there for, it's perpendicular to AI. So, perpendicular label there. And then, what did I do after that? So yeah, after I realized that perpendicularity, like, I noticed that, that means that IH, this should be H because it's telling us to prove it's the orthocenter. That would mean that this is tangent to the circle BIC from incenter excenter lemma. So that, because this is the center by the midpoint of arc BC is the center by incenter excenter lemma. So that means that if there's cyclic, it can't be tangent because yeah, if it's tangent, it's gonna be outside now. So I knew that it couldn't be 60 degrees. And then yeah, those random drawings were just me trying random stuff later. So I thought, okay, so that means that BK, since K is outside of circle BIC, because tangent, that would mean that angle BKC has to be smaller than angle BIC. Right? I think that was my reasoning at the time, something like that. So I just tried, okay, orthocenter angle less than in-center angle is bigger than 60. So, before I did that, or was it after I did that? Yeah, so yeah, I tried drawing it with an angle slightly bigger than 60 degrees. It was still kind of off. But yeah, at this point, I realized maybe I can trig bash this. Everything is trig. Everything here can be pinned down in terms of trig values. Like in center or orthocenter, and circumcenter, they work pretty okay with trig, sometimes ugly. And center's gonna be pretty ugly, but I thought it might be doable. So yeah, I started doing some trig stuff. So yeah, JD is BD minus BJ. BD is just the touch segment thing, so that's semi-perimeter minus B. By trig, BJ is just AB times cosine of angle B, and so on, and so forth, until I got that the concurrency happens if and only if this boxed equation is true. And then I was like, nope, this is too ugly. I will not bash this. So, I mean, I tried seeing if I could simplify it a bit more. Yeah, and then this is why, yeah, but this is why I wanted to show AK equals AH so that K and H become the same point, but no, it was too ugly. So I abandoned trig bash. And then so, yeah. After looking at the diagram for a while, I started thinking maybe I have to add something else. And I noticed that the line passing through I perpendicular to AI. If you hit that with AB and AC, they're the tangency points of the A mixtilinear in circle. So I thought maybe I should draw the mixtilinear in circle. So I drew it in, the thing tangent to AB, AC, and the circumcircle of ABC. I mean, I was like, I knew almost none of the properties of it, but I knew a bit, so I thought in case it's the actual solution, I tried it. But it didn't really get me anywhere, so I abandoned that, especially because I didn't really know anything about it. But then at this point, I noticed you have right triangle AIK, K supposedly the orthocenter. The midpoint of the segment AH often comes into play in a lot of problems regarding orthocenter and circumcenter stuff. Examples including last year's European Math Cup Junior problem number 3, the 7th one. I did really well that year, this year not so much. I mean, it's senior, of course I won't, but not as well. Anyway, so yeah. So the midpoint of the segment connecting the orthocenter and the vertex plays a role in a lot of problems involving orthocenters based on my experience. So I thought maybe I can let the M be the midpoint of segment AK. And then we also have the added bonus that angle AIK is 90 degrees. So this actually gives us the midpoint of the hypotenuse of a right triangle, which has some nice properties, being MA equals MK equals MI. M is the circumcenter of the right triangle AIK. So from here on, I started working a bit, and then it's well known that the altitude and the segment AO are isogonal conjugates. It's easy to angle chase. Angle BAJ is 90 degrees minus B, and then angle OAC is also 90 degrees minus B, because angle AOC is 2B, so each of OCA and OAC will be 90 minus B. So yeah, but I just said it's well known because I was trying to save time, but yeah. So it's well known those are isogonal. So segment AI would bisect angle KAO because they're reflections about the angle bisector. So you get here, see, they're both B minus C over 2. Angle MAI equals angle OAI. But then, these two are obviously parallel because these two are obviously parallel because DI is perpendicular to BC. The altitude is also perpendicular to BC. So yeah, parallel, interesting. But then here's where it gets more interesting. What again? You can actually show that after angle chasing a bit, like isosceles triangle. Oh, this angle is equal to that. Angle bisector, that angle is equal to that. And because angle OAI is equal to angle AIM, we get that MI and AO are actually parallel. Pretty cool, right? But remember, AO is also parallel to DK. So this actually gives us MI parallel to DK. Again, we also know these two are parallel. So this is in fact a parallelogram. But we can actually say more about this. We know MK equals MI. So it's not only a parallelogram, but also a rhombus. Nice, that really helps connect a lot of stuff. And then, so, yeah, and then after that, we get that all these 4 segments are equal, and also equal to this thing, and also equal to this thing, and all. And then, after that, so these two parallel, these two also parallel. So this is, again, another rhombus, because this also equals this. So you have 2 rhombuses just put on top of each other, which really adds a lot of structure to our diagram, and gives us much more stuff to work with. Then, after that, so I had AM equals MK equals ID. Then the thing I noticed is, oh, that means that the in radius is equal to half of the segment connecting A and the orthocenter, because this is supposed to be the orthocenter. But it's well known as a result of the Euler line that this is the length of the foot of the, this is the length of the line of the segment joining O to the foot of it on BC. So this must, here, like if M is the midpoint of BC, ON must be equal to ID, because ON is equal to half of this, because this should be orthocenter equals this. So, and this gave way to how you can draw the diagram properly. So you first start with a circle, then you have center, draw a random chord through it, preferably not through the, not through the center, otherwise you'll get isosceles. Then after that, you draw the line there, you can see I drew it really lightly, and then draw the perpendicular to that line, intersect it there. That should be your in-center, and then this should be your vertex A. Then after that, by using in-center, x-center lemma, we can just simply use our compass and whoop around there to get our B and C. And then I will be the in-center. From there, draw everything else as normally. And that's how you draw the diagram properly, which can really help you see things better. Drawing an important diagram is, drawing a good diagram is crucial for gaining insight in geometry. Anyway, that's my opinion. Probably is, I think. I don't know if you guys agree with me on that. And then, so yeah, after figuring that out, I managed to draw a better diagram. As you can see, everything lines up now. So what I need to show is that this equals this, which would, I thought at first, this two should be equal, because that would imply that this is equal to twice of this, which immediately implies that this is the orthocenter. Essentially proving AK equals AH, which is one of my ideas which is what I wanted during the trig bash. So anyway, at this point, I was a bit stuck. I was like, how do I prove that this is like 1/2 of that? And then I realized that these three are all parallel lines, you know, KD, MI, and AO, and M is the midpoint here. So if I draw those three parallel lines and hit it here, where's a pencil? And I hit it at BC at 3 points, D, N, and X. Then I must have that, because they're all parallel, and then these two are equal. These two should also be equal. We must have Dn equals Nx. And then at that point, I was like, how do I prove Dn equals Nx? That's like so random. N's midpoint, X is like some random line that goes nowhere. I mean, yes, it's the diameter. But in terms of diameter intersecting BC, that point has almost no properties. Or at least known properties to me. So this point I was a bit stuck. I was kind of staring at my diagram, cycling around different problems again. Then eventually, it struck me. Di equals It. Hence, T is the opposite of the diameter of the DT is the diameter of the incircle. And it's well known from chapter 4 of Evan Chen's geometry book that if you draw the diameter of the incircle like that and hit it on side BC, that has to be the AX touch point. X is the AX touch point. The proof of this is simply, let's look at this diagram here for now. So you see the incircle DEF, it's a bit messy. Point T is up there. This one's your T. So you draw a line through T parallel to BC. So you get that, and then let it hit their B prime, C prime. So you get triangles AB prime, C prime, and ABC are similar. Then you notice that DEF, circle DEF, this incircle, is actually the X circle of this triangle. So by homothency, if you like whoosh it out, this circle whooshes out to the X circle of the big triangle. Hence, T should also whoosh out to the AX touch point. So another way to prove this is simply saying, oh, these two triangles are similar, and clearly B prime T over TC prime is equal to BL over LC. So like T and L must be corresponding points in the triangles. T is AX touch point here, so L is, well, I labeled it X in the other diagram. So L here should also be the AX touch point. So yeah, that's just, homothency is just a fancier way of saying it. Why didn't I just say it by similar triangles earlier? But anyway, so yeah. So now we get This is the X touch point. But then it's also well known by Evan Chen's book once again. I don't forgot if this was chapter 2. That if you have the in touch point here and the X touch point here, BD equals CX. Hence, if I let MI intersect here at N, not knowing it's the midpoint, saying if I let MI intersect there at N, then I get DN equals NX due to the parallel, due to these two being equal and all the parallels. I also get BD equals XC due to the, what do you call that again? Due to the lemma on the in touch and X touch points. Then that gives me BN, this plus this is equal to this plus this. So BN is equal to NC. So like, this proves that MI passes through the midpoint. Yay! Now what does that give us? MI parallel to AO and AM parallel to ON. ON is perpendicular to BC because we now know that, because N is the midpoint. And then so like, now that gives us parallelogram AM and O. And that gives us ON is equal to AM, which is clearly 1/2 of AK. And that now proves that AK has the length that AH should have if H were the orthocenter. Hence, K is indeed the orthocenter, and they must concur at the orthocenter. QED.